Welcome to the revision session on power system. So first we will see power system analysis part. As we already discussed, power system analysis means we need to see per unit system, symmetrical components and sequence networks, fault analysis, stability analysis and load flow analysis. First we will see per unit system, then we will go to symmetrical components, and then fault analysis, stability analysis and load flow analysis. Okay, so in today's session I'm going to cover per unit system, symmetrical components and sequence networks. So tomorrow's session we will see fault analysis and then stability and load flow analysis. So that is a plan. So that means it is a 3-day session. In these 3 sessions we are going to complete the power system analysis part. So as we already know that power system analysis is very important for the GATE exam. So definitely you will get 5 marks from this topic. So that's why careful with the power system analysis part. Okay, now coming to the first topic, which is per unit system. As we already discussed, per unit value means it is the actual value of the quantity divided with the base value of the quantity. So actual value divided with base value is the per unit value. But the first important thing in per unit system is, see, actual value, base value having same units. Okay, so that's why per unit value is unitless. For example, let's say the actual voltage is 10 volts and base voltage is, let's say, 100 volts. If that is the case, what is the per unit value? So V per unit can be written as 10 by what? 100 volts. 10 volts by 100 volts. So volts get cancelled. So that's why per unit value generally unitless. So what are the per unit value here? What is the per unit value here? I can say 0.1 per unit. Okay, that is the per unit voltage. So the first important thing is, so actual value, base value having same unit, so per unit value is unitless. And the second thing is, the per unit value may be greater than 1, may be less than 1 or may be equal to 1. Okay, so per unit value may be greater than 1, may be less than 1, may be equal to 1. Don't say that per unit value is always less than 1. That's not correct. Okay, so how to justify this? For example, we have a 100 MVA 11 kV synchronous generator. 100 MVA 11 kV synchronous generator we have. Okay, so this is the generator which is having rating of 11 kV 100 MVA. See, what is the full load current or rated current, which is 100 into 10 power 6 by root 3 into 11 into 10 power 3, we get 5.24 kilo ampere. That is the rated current. Correct or not? The rated current or base current, both are same. S base by root 3 times V line base. So but the default base is the rating of the machine. That's why I base, if you substitute and you check, you get 5.24 kilo ampere. Now if I ask the current, what is the full load current? That means if the machine is fully loaded, how much will be the current? Full load current will be same, 5.24 kilo ampere. That means if the machine is operating under rated load, what is the per unit value? The per unit value is 1. Suppose if the machine is operating at 50% of the rated load, think about, then what is the current, load current? 5.24 by 2 kilo ampere. So that means the per unit value less than 1. Yes, it is possible. Suppose if the machine is delivering a fault current, for example, if there is a 3-phase fault at the generator terminal, approximately the subtransient fault current is 10 times the full load current. If it is 10 times the full load current, means 52.4 kilo ampere. That means what is the fault current in per unit? That is 10 per unit. That means greater than 1 possible. That's why during fault, generally the per unit value is greater than 1, generally speaking. If the machine is operating less than the rated capacity, if the machine is delivering a load less than the rated capacity, then per unit value less than 1. If the machine is fully loaded, then per unit value is what? Equal to 1. So these are the things we need to understand about the per unit system. So per unit value may be less than 1, may be greater than 1, may be equal to 1 possible. Next, default basis rating of the equipment. Just now we discussed. For example, we have 11 kV 100 MVA generator. 11 kV 100 MVA generator. What is S base? S base means what? It's not complex power base. Careful. It is an apparent power base. The apparent power base is how much? 100 MVA. What is the line voltage base? That is 11 kV, because the rating of the machine is what? It's 11 kV 100 MVA machine. 11 kV 100 MVA machine means by default, if it has not mentioned, means yes, the voltage base is 11 kV and MVA base is what? 100. That's what we need to understand. That's what the meaning of the note number 3. So the default base is always considered to be the rating of the equipment. Next one is, this is a very important thing, sir. Base value having only magnitude, phase angle is same for actual value and per unit value. Okay, so if you notice this point, what I'm saying is, base value having only magnitude, phase angle is same for actual value and per unit value. So what the meaning is, for example, if I say actual voltage may be something like this, 10 at an angle minus 30 degrees. This is what actual value, because in AC system the actual voltage means it's a complex number which has a magnitude and what? Some phase angle. Okay, correct or not? So the phase angle is what? Minus 30 degrees here. For example, let's say this is volts. Now, if I want to select the base quantity, shall I select like this, 100 at an angle minus 30 degrees? This is not correct. The base quantity is always having magnitudes, no phase angle for base quantities. Careful about this. Voltage base, 100, maybe 100 at an angle something, that is blender. Okay, so this is not correct. Now I can select the base voltage something like this, 100 volts. Yes, that is correct. So that's why what I can say here, what is V per unit? V per unit equal to V actual by V base. If it is V actual by V base, then what I get now? 10 at an angle minus 30 degrees divided with 100. If I solve this, we get 0.1 at an angle minus 30 degrees per unit. So what you can understand from here, the actual value and what? Base value, if you notice, actual value having a magnitude and phase angle, but base value always having magnitude. That's why the phase angle of the per unit value, the phase angle of the actual value, just notice, same. The phase angle of the actual value, phase angle of the per unit value are always same. That is the next important thing in per unit system. Okay, now note number 5, the percentage value equal to per unit value into 100. Okay, for example, let's say V per unit is given to me is 0.5. V per unit is 0.5 per unit. What is percentage V? Let's multiply this 0.5 with 100. Then that gives what? The percentage value. Now tell me what is the percentage value here? 50%. So similarly, if percentage value is given, you can convert back to per unit value. Generally, so the machine data will be given like this. The subtransient, transient and steady state reactances of 11 kV 100 MVA generator are 10%, 50% and 110% respectively. That means percentage values are given, but generally we solve with what? Per unit value. So you divide the percentage value with 100 before doing any calculations, so that we get a per unit value. That is the idea. Okay, so this formula also very important. The next important thing is addition, subtraction, multiplication and division are possible with per unit quantities. That means if you have two per unit numbers, let's say x1 equal to 0.1 per unit, x2 equal to 0.2 per unit. Now I want to calculate the x, that is what? X1 plus x2, that is a relation. Okay, if that is the case, I can directly add the per unit numbers. The resultant is per unit value. Okay, for example, I want to calculate y, that is x1 into x2 into x1 or x1 into x1. Okay, whatever it may be. Then yes, I can do x1 into x2 will give you what? Again y, that is also a per unit number. That means the multiplication, division, addition and subtraction you can directly do on per unit numbers, but you cannot do on what? Percentage numbers. See, strictly speaking, addition and subtraction you can do, possible for what? Percentage numbers, but multiplication and division not possible with what? Percentage quantities. This is what you need to notice. So for understanding this, I am just considering an example. Let's see. So let's say R1 is 50%, R2 is 10%. Now tell me, if R1 and R2, these are the resistances, R1 and R2 are connected in series, R1 and R2 is connected in series, then what is R equivalent? R equivalent is what now? R1 plus R2. So if I directly do this operation on percentage numbers, what I get now? 50 plus 10, 60 percentage. Let's do with per unit numbers. What is R1 per unit? 0.5 per unit. What is R2 per unit? 0.1 per unit. Okay. Now tell me, what is R equivalent in per unit? What is R equivalent in per unit? 0.1 plus 0.5, which is 0.6. Now tell me, what is R equivalent in percentage? Just multiplied with 100. So we get what? 60 percentage. What I can say, we can do the addition operation, similarly subtraction also on percentage numbers. Okay. But we cannot do the multiplication and division on percentage numbers. For that I am giving one more example. Let's have a look. For example, let's say the percentage R is given 10 percentage. Percentage I is given, let's say 20 percentage. Now I am asking, what is the percentage value of V? Let's do directly. Percentage V equal to percentage I multiplied with percentage R. Suppose if you are doing like this, then what I get? We get 200 percentage. Okay. Clear? This is not at all correct. Okay. Now have a look. What is V per unit? If I do it in per unit, V per unit is 0.1 into R per unit multiplied with I per unit. I am doing 0.1 multiplied with what? 0.2. That will be 0.02. 0.02. Now tell me, what is percentage value after this? Percentage V equal to 0.02 into 100, that is 2 percentage. 0.02 into 100, that is 2 percentage. So from this, what you have understand, or what we can understand is, see, multiplication and division we can do it on what? Per unit quantities, not with percentage quantities. So that's why, sir, whatever may be the mathematical operation, it might be multiplication, division, addition or subtraction, do it with per unit numbers. Later, by multiplying with 100, we can get what? Percentage numbers. Okay. So that is the next important thing in per unit system. Next, have a look. Per unit analysis on single phase system. Okay. So in single phase system, if you want to do the per unit analysis, okay, the first important thing is, basically we have 4 variables, sir. S base means, what is S base? Complex power base or apparent power base? See, complex power means generally, for example, complex power is S. That is, we can write P plus JQ, which has a real part and imaginary part. So, which has a magnitude and what? Phase angle. And phase angle is tan inverse Q by P. Correct or not? This is how we can convert S into what? Polar form. Simple complex number. So, a complex number having a magnitude and phase angle. But the magnitude of the complex number, this is a magnitude. This is called what? Apparent power. Correct or not? Apparent power. So, that is simply magnitude of S. Okay. So, this is called apparent power. See, we know that base quantities always having magnitude, no phase angle for base quantities. That's why when I say S base, that is not complex power base. That is what? Apparent power base, because apparent power not having any phase angle, but complex power having some phase angle. So that's why S base means it is an apparent power base. 100 MVA is the S base. Correct or not? Clear? So we need to say it is what? Apparent power base. Next, so V base, I base and Z base. But careful, while selecting the S base and V base, I base and Z base, these equations should satisfy. These equations should satisfy. For example, let's see, I selected S base is equal to 100 volt ampere, and I selected V base equal to 100 volts, and I base equal to 10 ampere, and Z base equal to, let's say, 10 ohms. Check. See, if I multiply V base and I base, I should get S base. What is V base and I base multiplication? 1000 volt ampere. But what you are selected? 100 volt ampere. Is this correct? No. And V base by Z base is what? I should get 10 ohms. Yes, we are getting 10 ohms, but S base is not satisfied. But tell me, is this the correct way of selection? No, this is not at all correct. You must select the base quantities such that the relations, fundamental relations should satisfy. Okay, clear? These are the relations for actual quantities and base quantities as well. But careful, in actual quantities, the voltages and currents having some magnitude and phase angle, but when it comes to the base quantities, they are just having only magnitude. Okay, so that's why the point is, so this is not the way of selection. That's why, so to satisfy the fundamental equations, let's fix two variables and the remaining two variables you need to calculate. That is the fundamental rule. Okay, what are the two variables I am fixing? Apparent power base I am fixing, and also what? Apparent power base I am fixing. Then voltage base I am fixing. Is there any reason to select known base is S base and V base? Very simple, sir. Why I am saying known base is S base and V base is the default rating of any equipment you see, the voltage rating is given and what MVA rating is given. That means if you see the nameplate details of generator or transformer or transmission line, these are the two ratings are available. So many ratings are available, but fundamentally these two ratings are what? Common for every electrical equipment in power system. What are the two ratings? Apparent power and what? Voltage rating will be given. For example, let's say 11 kV 100 MVA synchronous machine. There is a synchronous generator whose rating is 11 kV and 100 MVA. So that means, so directly you know the S base, that is 100 MVA, and directly you know the line voltage base, that is what? 11 kV. Correct or not? So that's why known base is S base and V base, and unknown base is what? Z base and I base. That's what we need to calculate. Okay, but how to calculate I base in terms of S base and V base? We know that I base equal to S base by V base, and Z base is what? Simply V base whole square by S base. That's it. Now similarly, let's see what is V per unit. V actual by V base. What is I per unit? I actual by I base. But what is complex power in per unit? The complex power in per unit, is what? S actual by S base. But what is S actual? P actual by J times the Q actual. And S base is okay, fine, it's only magnitude. I can divide like this: PA by S base, J times the QA by S base. Now this is nothing but what? P per unit. Now this is nothing but what? Q per unit. So what you can understand here, there is no concept of P base. For example, P actual is, let's say, 50 megawatt. I can't say P base is some 100 megawatt. This is not valid. Only S base is valid. For example, S base is 100 MVA. Now what is P per unit? 50 by 100. That is 0.5 per unit. So that's why the point is clear. There is no concept of P base and Q base. Because when you write P base and Q base means mathematically you need to write P base plus J times the Q base. Correct or not? Suppose you are defining P base and Q base. Think about it. Then you can define S base, P base plus Q base. But S base having what now? Magnitude and phase angle. Is that correct? No. That is why no concept of P base and Q base. Only it is what? S base. And similarly, there is no concept of what? There is no concept of R base and X base. Because if you want to say R per unit is what? R actual by Z base. X per unit is what? X actual by Z base. So that's why the point is clear here. There is no concept of R base. There is no concept of reactance base. Only it is the Z base. Okay. So that's why R base, X base, P base, Q base are not valid. Okay. What is valid? Z bases exist and what? Apparent power bases exist. Okay. Clear? So that is the next important thing in per unit system. Next, per unit analysis of single phase transformer. Okay, this is very simple. We already discussed. The single phase transformer means basically three ratings are given. The primary voltage rating is given, secondary voltage rating is given, and what? Apparent power, which is same for what? Both primary and secondary. So the ratings are considered as default base. Now what is the formula, sir? K equal to transformation ratio is the K that I can define N2 by N1, V2 by V1, I1 by what? I2. The same transformation ratio is also valid for what? Base quantities. But the only difference is maybe this actual voltage is having magnitude and phase angle, but the base voltage is only having magnitude. That you have to notice. Now what is the K now in terms of base? V2 base by V1 base, I1 base by what? I2 base. That means you can write V2 base equal to K times the V1 base. I can write I1 base equal to K times the I2 base, and similarly I can write Z1 base equal to what? Z2 base by K square, and we can write Z2 base equal to Z1 base into what? K square. These formulas are always valid. Okay, because these formulas are valid with the original system, I mean to say actual system, and also valid with what? The base also. Okay, so for a transformer in per unit form, so I'm not going to prove this. Careful. V1 per unit equal to what? V2 per unit. I1 per unit equal to what? I2 per unit. And Z01 per unit equal to what? Z02 per unit, which is equal to Z1 per unit plus Z2 per unit. Now careful here, sir. Z01 means it is the impedance referred to primary. Okay, so I can write like this in actual form. This is the transformer equivalent circuit. See, Z01 is the impedance referred to primary. But what is Z1 and Z2? Z1 and Z2 means I can draw the equivalent circuit like this. This is Z1, this is Z2. This is the primary impedance of the transformer and secondary impedance of the transformer. Okay, that's why nomenclature you should be very careful in the problem. If something is given means you need to understand whether it is Z1 or Z2 or Z01 or Z02. If I want to mention Z01 in the problem means I will clearly say the impedance of the transformer referred to primary. If I want to mention Z02, I will clearly say in the problem saying that the impedance of the transformer referred to secondary. Suppose if I want to say Z1 and Z2, what I will say? The impedance of the transformer of primary, otherwise primary impedance of the transformer, otherwise secondary impedance of the transformer. That's why careful, sir. Okay, but if you add primary impedance in per unit and secondary impedance in per unit, that is equal to Z01 or what? Z02. That means for a single phase transformer, the impedance of the transformer referred to primary, the impedance of the transformer referred to secondary are always same. Similarly, in per unit form, the voltage in primary, the voltage in secondary are always same. And also in per unit form, current in primary and current in secondary are always same. So apart from this, what I can say is, in per unit system, we can define K in per unit form. That is V2 per unit divided with what? V1 per unit. What is this value? Always equal to 1. Okay, K in per unit form, V2 per unit by V1 per unit. Okay, so that's why, so the idea is here, if you want to write a Z01, simple way to prove, Z01 per unit equal to what? Z02 per unit, people will say that by K square, but K must be what? In per unit form, right? In per unit form, this is equal to what? 1. That's why Z01 per unit equal to Z02 per unit. That's why, so when you draw the equivalent circuit of the transformer, we draw like this in actual form. Correct or not? This is Z01 in ohms. This is the equivalent circuit of the transformer referred to primary. Okay, this is in what? Absolute form. Here what? Some transformation ratio K. That means this voltage and this voltage are not equal. Okay, but in per unit form, what I say? Simple equivalent circuit. There is no concept of coupled circuit when you are drawing the equivalent circuit of transformer in per unit form. Coupled circuits are not coming into picture. Why? Because this point and this point having same potential. Because V1 per unit, V2 per unit are same. I can join like that. If the per unit voltages are same, I can join like this in per unit form. So that's why there is no concept of coupled circuits. Okay, when it comes to the transformer equivalent circuit. Okay, that's why the per unit system is very simple. Okay, but in absolute system, what happened? There exists a coupled circuit in transformer equivalent circuit. So that's why the analysis become so bit complex. That's why per unit system is more advantage than absolute system. That's why all the analysis means fault analysis, stability analysis and load flow analysis we carried out in per unit form, not in absolute form. Okay, so that's about the per unit analysis of single phase system. We have seen per unit analysis of transformer as well. Now we will go to the per unit analysis of three phase system. But when it comes to three phase system, there are two variables extra added here. I told you basically four variable: S base, V base, I base and Z base. Okay, S base means fine, right? Z base means fine. Z base means always it's a per phase impedance. Okay, but when I say voltage base, there may be line voltage or there may be phase voltage. If I say current base, there may be a line current and phase current. But line voltage and line voltage and phase voltage, line current and phase currents may be same, may not be same. That depends on the connection what you are dealing. For example, if it is a star connection, line voltage, phase voltage not same. For example, if it is a delta connection, line current and phase currents are not same. That's why better to define all the possible things like S base, line voltage base, phase voltage base, line current base, phase current base and what? Z base. So these are the things we are going to define now. Have a look here. But it might be star connection or delta connection. These relations are valid. S equal to what? Root 3 into V line into I line. Careful. This is three phase apparent power. This is line voltage magnitude, line current magnitude. Because apparent power means what? You have to select only magnitudes of voltages and currents. Okay. So otherwise you can write 3 into phase voltage magnitude and what? Phase current magnitude. Okay. Now what is Z base? Careful, Z base is always phase voltage by phase current. There is no concept like Z base or Z equal to V line base by I line base. This is a blunder. For star connection or delta connection, this is not valid. Z is always a per phase quantity. You need to define the Z is nothing but phase voltage by phase current. There is no concept like line voltage by line current. Z is always a per phase quantity. Careful about this. Now again the same thing. What are the known bases for us? Yeah, S base and V base are the known base. These are the two known bases for us. Okay, and what are the unknown bases now? What are the unknown base? Unknown is what now? I can write like this. Unknown is what? V phase base is unknown. It might be star connection or delta connection. V phase base is unknown. Then I line base is unknown. I phase base is unknown. And Z base also unknown. Now these are the four unknowns, only two knowns. Now let's see if it is a star connection, sir. For a star connection, phase voltage equal to line voltage by root 3. Correct or not? But at an angle minus 30. But shall I consider minus 30 now? No. Why? We have deal with only magnitudes here. As I told you already, base quantities having only magnitude. Suppose if it is a 11 kV star connected load. 11 kV star connected load. What is V line base? That's it, 11 kV. What about V phase base? 11 by root 3. But don't say 11 by root 3 at an angle minus 30. That is not correct. Clear? So the point is we are going to consider only magnitudes. Anyway, fine. What about the line current equal to phase current? Now, what about line current and phase current? They are equal. So that is equal to S base by root 3 times V line base. Okay, from this. I line base equal to S base by root 3 times V line base. So anyway, I phase base also same. So we are calculated I line base and I phase base in terms of known thing, S base and V line base. Similarly, Z base equal to V phase base and I phase base. Okay. Now if you substitute I phase base and if you substitute V phase base as V line base by root 3. V phase base is V line base by root 3 here. And I phase base is nothing but what? S base by root 3 times V line base, and finally we get Z base equal to V line base whole square by S base. So the Z base is V line base whole square by S base. Careful about that. That is the Z base value for star connection. Now coming to the delta connection here. See here V phase base and V line base are same. Why? Since it is a delta, phase voltage and line voltage are same. So V phase base equal to V line base. But what about I line base? Yes, S base by root 3 times the V line base is what? I line base. Using same formula, because these are the formulas valid for what? Valid for both star and delta connection. Basically we have a star connection or delta connection in power system, in 3-phase system means. Correct or not? Anyway, so these formulas are valid for both star and delta connection. That you have to notice. Okay. And now what is I line base? S base by root 3 times V line base. What is I phase base? I phase base is I line base by root 3. So I line base by root 3 means S base by root 3 times the V line base by root 3. So that's why we get here 3. S base by 3 times the V line base. Now Z base equal to what now? V phase base by I phase base. Okay, V phase base equal to V line base. Okay, so that's why if I solve, I get here 3. Careful about this. Z base here is 3 into V line base whole square by S base. But here Z base, V line base whole square by S base. Okay, so the simple example here is, for example, have a star connected load. Which is supplied from 11 kV 100 MVA system, and here the resistance is 1 ohm. A star connected load, resistance is 1 ohm, which is supplied from 11 kV 100 MVA system. What is Z star per unit? What is Z star per unit? 1 by V line base, 11 square by 100 MVA. Z base, if you need, Z base you need to calculate. Z base equal to what now? For star connection, 11 square by what? 100, that is 1.21. So 1.21. Okay, that is for Z star in per unit. Now if I convert this into Z delta, if I convert that into Z delta, so what is Z delta? We get 1 ohm na here. What is delta impedance? Okay, delta impedance will be what? 3 times the star impedance. We get here 3 ohms. All are 3 ohms. Now tell me, what is Z base for delta connection? Z base for delta connection is 3 times KVB base square by MVA base. So how much you get? 3 into 1.21. Now tell me, what is Z delta per unit? Z delta per unit is equal to 3 by 3 into 1.21. That means 1 by 1.21 per unit. So from this, what I can understand, Z star per unit and Z delta per unit are always same. Okay, so that means, if for example, if the question is given, there is a star connected load, the per unit impedance of star connected load is 1 per unit. Now if this star connected load is converted to delta, what is the per unit impedance per phase? Same, 1 per unit only. Careful about this. This is very, very important. That means when you convert star to delta, okay, the per unit impedances will not change. I am saying 3-phase star to 3-phase delta. Okay, when you convert 3-phase star connection to 3-phase delta connection, the per unit impedances will remain same. That you need to accept. Okay, clear? Now we go for the per unit analysis of 3-phase transformer. See, per unit analysis of 3-phase transformer means, the first important thing is, if it is a 3-phase transformer, definitely what is given? The primary line voltage, secondary line voltage, and what? MVA rating. Okay, so transformation ratio is nothing but the phase voltage in the primary by phase voltage in the, phase voltage in the secondary by phase voltage in the primary. Otherwise, phase current by in the primary by phase current in the secondary. So you need to select only phase, not the line. So if I define transformation ratio as V2L by V1L, for example, if I define like this, this is blender. Okay, the transformation ratio is always valid with respect to phase quantities, not valid with respect to line quantities. Okay, now for example, let's say it is a 11 kV by 132 kV transformer. Okay, let's say it is a star delta transformer, for example. Now I am asking to calculate what is the transformation ratio. The transformation ratio that is 132 by 11 by root 3. Okay, 132 by 11 by root 3. Why we have done 132 by 11 by root 3? Very simple. Okay. Yeah, 132 by, it is why it is 132 by 11 by root 3? See, in case of secondary voltage, it is delta, na? That's why line voltage and phase voltage are same. Yes, we need to substitute here phase voltage. But 132 kV is the line voltage. But delta, that's why phase voltage is same as line voltage. But star side what? 11 kV is the line voltage, but I want phase voltage, that's why 11 by root 3. Okay, so that's how you need to calculate the transformation ratio. Clear? So these things are also very important here. See, for a transformer, that means for a three-phase transformer, next important thing is, for three-phase transformer, if you notice, no matter whether it is star delta or delta star or star star or delta delta, whatever may be the transformer connection, V1 phase, V2 phase always same. Phase voltage in the primary, phase voltage in the secondary always same, and even there is no phase shift. The magnitudes are same, and what? Phase angles also same. Okay, clear? Similarly, I1 phase, I2 phase also same. Z01 per unit and Z02 per unit is always same, no matter whether it is star delta, delta star or star star or delta delta connection. But when you see the line voltage in the primary and line voltage in the secondary, see, there exists a phase voltage primary, phase voltage secondary, correct or not? Apart from that, what? Line voltage in the primary, line voltage in the secondary, and also line current in the primary, line current in the secondary. But those relations you should be very careful. See, for star star and delta delta transformer, V1 line and V2 line are same, and I1 line and I2 line also same. Both are in what? Magnitudes and what? Their phase angles. But for a star delta transformer, if you see, star delta transformer, V1 line equal to V2 line at an angle plus 30 degrees. That means there exists a phase shift of what? 30 degrees. So V1 line magnitudes are same, but the phase angle is what? 30 degrees. Similarly, I1 line and I2 line in per unit form are same, but there is a phase shift of what? 30 degrees. Okay. Similarly, delta star transformer, here minus 30 we get. So the idea is simple here. For star star and star delta transformer, sorry, for a delta star and a star delta transformer, there is a phase shift of 30 degrees, but for a star star and delta delta transformer, so between line quantities there is no phase shift. Clear? So these also very very important about our three phase transformer in per unit form. Clear? So the next important thing is, this is one simple thing you need to note. If three single phase transformers of each rating V1 by V2, S and X per unit, that means what? It is a transformer, the primary voltage is V1, secondary voltage is V2, MVA rating is S, and its per unit reactance is X per unit. For example, let's say 10% or 10%, nothing but 0.1 per unit. Okay. If I convert this three single phase transformer to form a three phase transformers, that means I have a three single phase transformer, transformer 1 and transformer 2 and transformer 3. I am just making them 3 to form what? A three phase transformer. Three single phase transformers I can reconnect to form a three phase transformer, that I can do. Okay. But if I do like that, MVA rating will be what? 3S. What is the meaning here? If MVA rating of the single phase transformer is, let's say, 10 MVA, then the MVA rating of three phase transformer is what now? 30 MVA. Clear? No matter what is its connection, irrespective of its connection, this is what? True. So irrespective of its connection, these things are true. And what about per unit reactance? Per unit reactance of each single phase transformer is 10%. Now here also same. So that means 10% means in per unit form 0.1 per unit. The per unit reactance will not change. Okay, if I convert three single phase transformer to what? A three phase transformer. But voltage ratings, careful, is based on the connection. Because see, voltage rating for three phase transformer, Voltage rating of a three-phase transformer is what? Line voltage by line voltage. Correct or not? But single phase transformer by default it is a phase voltage. That you need to accept. Correct or not? So if I say this is what? This is by default phase voltage. By default here phase voltage. But now when I say three-phase transformer, you have to show line voltages. Correct or not? And now tell me, if it is star-star connection, phase voltage is V1, but line voltage will be root 3 times the V1. So primary voltage rating is root 3 times the V1. Secondary voltage rating is also root 3 times the V1. Now if it is a star delta transformer, yes, primary voltage rating is root 3 V1, but secondary voltage rating is V2. Why? Because phase voltage is V2, line voltage also V2 for delta connection. So based on that logic, we can write the remaining 2. So this is what a very, very important thing again. Okay. So please pause the video and you need to write all these formulas. First you need to see the formulas and practice all the formulas. Okay, without seeing what the board. Okay, I hope you understand. So the revision should be like this. So all the formulas what I am listed here, you have to write again on your notebook. Don't think that your time is wasting. Okay, but you have to write all these formulas. Once you listen this, you need to write all the formulas without looking into the board, and you need to check whether you are written correct or not. So that is how you need to improve yourself. Okay, so I'm going to cover all the formulas which are there in per unit system. Okay, anyway, so the next one, the last formula, yeah, Z per unit new equal to what? Z per unit old into KVB old whole square by KVB new whole square, MVAB new by MVAB old. So what you can understand from here, see, generally we are coming across the changing of base quantities. For example, let's say I have a transformer and generator. See, it is a 11 kV 100 MVA generator which is connected to maybe 13.8 kV by 132 kV transformer of 150 MVA. Now which is per unit impedance 0.1, here per unit impedance is 0.2, for example. See, you have to do the analysis on this network, fault analysis for example. Then you must convert the generator and transformers must be on common base. Common base means, for example, I have selected generator rating as base. Okay, if you select generator rating as base, generator per unit reactance will remain same. But what about the transformer per unit reactance will change? The transformer per unit reactance new equal to the old value multiplied with KVB old. Since this generator is on the LV side of the transformer, so you need to see LV side. What is KVB old? Rating of the transformer. So 13.8. What is KVB new? Since we are selected the generator rating as base, 11 whole square. MVAB new is 100. MVAB old is what now? Its rating 150. So this is how we need to convert the reactances onto a common base or impedances onto a common base. Once you done that analysis, then then we can go for any type of analysis. It might be fault or stability or load flow analysis. So when you are doing analysis, the reactances or impedances of all the elements must be converted onto a common base. So for that conversion, this formula playing a very, 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 very important role. Okay, clear? So that's about per unit system. With this, I'm concluding per unit system, and the next topic is symmetrical components. The next topic is symmetrical components. See, the first thing we need to define in symmetrical components is balanced system. Okay, so we come across symmetrical components if system is unbalanced. Correct or not? To solve an unbalanced power system in easy way, the symmetrical components are introduced. Suppose if it is a balanced system, I can define VA, VB, VC. What is VA? VA at an angle 0, I can write V. VB is V at an angle minus 120 degrees, I can write alpha square V. Okay, alpha square is 1 at an angle minus 120. And VC is V at an angle plus 120, that is alpha times V. Okay, now apart from that, we can define a parameter alpha. These things are very important, please review. Okay, alpha square and alpha cube is 1, alpha power 4 is alpha, alpha power 5 is alpha square. That means anything power alpha can be written in terms of either 1 or alpha or what? Alpha square. Okay, anything power alpha. Okay, and alpha conjugate is what? Alpha square. Alpha square conjugate is alpha. 1 by alpha, alpha square. 1 by alpha square is alpha. And similarly 1 minus alpha is what? Root 3 at an angle minus 30. Alpha minus 1, root 3 at an angle 150. Similarly you can review all these terms which are very, very important. Okay, now the next thing is, suppose if it is an unbalanced system. So if it is an unbalanced system, every phasor, it might be voltage phasor or current phasor, can be written sum of positive, negative and zero sequence component. Let's say VA can be written as VA0, VA1 and what? VA2. And VB can be written as VB0, VB1 and VB2, and VC can be written as VC0, VC1 and VC2. But what is the relation here? If it is a positive sequence, the positive sequence consists of how many phasors? 3 phasors, maybe voltage or current. So VA1, VB1 and VC1. Why I am saying it's a positive sequence? Since it is following ABC sequence, that is the original sequence. So a positive sequence consists of 3 phasors equal in magnitude. If you see VA1, VB1, VC1, magnitudes are what? Same. But the phase displacement by 120 degrees. Clear? So VA1 we can written as V1, VB1 we can written as alpha square V1, VC1 we can written as alpha V1. So if we add VA1, VB1 and VC1, that is definitely equal to 0. Similarly, negative sequence means which has a sequence of what now? A, BC or ACB? It's not ABC. I'm sorry. This is ACB sequence. Okay. Have a look. ACB sequence, because first A, then C, then B. Clear? So what I can write now? VA2 is V2 at an angle 0, simply V2. VB2 is what? Alpha V2. What about VC2? Alpha square times V2. So VA2 plus VB2 plus VC2 is again 0. And so if you really notice zero sequence again, which has 3 components, VA0, VB0, VC0, but they are what? Also called cophasal components, because the phase angle displacement between them is 0. That's what the zero sequence definition. And VA0 plus VB0 plus VC0 is equal to 3 times the VA0. And sometimes he may ask you, what is residual voltage? Residual voltage means if you add VA, VB, VC, that is called residual voltage. If I add what is VA? This. VA1 plus VB1, VC1 0. VA2 plus VB2 plus VC2 0. And VA0 plus VB0 plus VC0 will be what? 3 times the VA0. The residual voltage is always the zero sequence voltage. Okay? Clear? Because if you add A phase voltage, B phase voltage, C phase voltage, positive sequence voltages sum in all phases will become 0. Negative sequence voltage sum of A and B and C are 0. Just now we have proved VA2, VB2, VC2 0, VA1, VB1, VC1 0. So that's why only VA0, VB0 and VC0, that is not equal to 0, that is VA0, 3 times the VA0. That's for residual voltage, for example given 300 volts. What is the zero sequence voltage of A phase? 100 volts. Zero sequence voltage of B phase? 100 volts. The zero sequence voltage of C phase also 100 volts. That's what you need to understand. Okay. So, and the next important thing is, see, we can write the relation between the sequence components with what? Unbalanced phasors. The unbalanced phasor is VA, VB, VC. So we can write, okay, VA0, VA1 plus VA2, that is as it is. But what about VB0? Can also written as VA0 plus. What about VB1? Check. VB1 equal to what? Alpha square V1. What about VB2? VB2 is nothing but what? Alpha times VA2, nothing but alpha V2. Similarly, we can write here VC0 also VA0, then alpha VA1. Check, sir, if you have any doubt. What about VC1? Alpha VA1 plus. What about VC2? Alpha square times VA2. Now we can write in matrix form VA, VB, VC. That is equal to, in terms of what? Sequence components. VA0, VB0 and what? Sorry, VA0, VA0, VA1 and what? VA2. How to write that? See, VA equal to VA0 plus VA1 plus VA2, that's why in the matrix here 1, 1, 1. Correct? then VB is what? VA naught plus alpha square VA1 plus alpha VA2. VC, VA naught plus alpha VA1 plus alpha square VA2. So this is called unbalanced voltage matrix. Now this is sequence transformation matrix T. Okay, now this is what? Sequence matrix Vs. Unbalanced voltage matrix VP or primary voltage matrix, and this is sequence transformation matrix, and this is the sequence voltage matrix. So what you can understand here, we can write like this: VP equal to T times Vs. Correct or not? Clear? So what I can say, we got VP equal to T times Vs. Correct or not? That is the relation between unbalanced phasors and sequence voltages. So we know what is VP. VP means what? Let me write again here: VA, VB, VC. That is equal to 1 alpha square alpha 1 alpha alpha square times VA naught VA1 VA2. Clear? So now if you want to write VS in terms of VP, so what I can write now? So VS can be written as T inverse times VP. Clear? So that is a relation between sequence voltages and unbalanced phasors. That means Vs can be written as T inverse times Vp. So what is Vs? Again VA naught, VA1, VA2. That is equal to 1 by 3 times T inverse. I am directly writing 1 alpha square, 1 alpha square. One alpha square alpha times that's it. But one thing you need to notice here, the expressions for VA naught is what? Directly 1 by 3 VA plus VB plus VC. The expression for VA1 1 by 3 VA plus alpha VB. The expression for VA2 VA plus alpha square VB. That's about VA naught, VA1 and VA2. Okay. So generally in the problem, VA, VB, VC given. For example, if VA, VB, VC given, it may ask you that what are the sequence components of phase A voltage. If the sequence component of phase A voltage means VA naught, VA1 and VA2, you need to calculate. Suppose if the question is calculate the sequence component of all phase voltages, you need to calculate VA naught, VA1, VA2. Then you need to calculate VB naught, VB1, VB2. Then you need to calculate VC naught, VC1 and what? VC2. But you know what is VB naught? VB naught is VA naught. What is VB1? Alpha square VA1. What is VB2? Alpha VA2. Then what is VC naught? Again VA naught. What is VC1? Alpha times VA1. Then what about VC2? That is alpha square times VA2. We already discussed these relations. Okay. So first you need to calculate VA0, VA1, VA2. Later what? We can calculate VB0, VB1, VB2, VC0, VC1, VC2 using simple relation. That means it's just a matter of alpha multiplication. Okay. So that's about the relation between sequence voltages and unbalanced phasor. Similarly you can write for current. Okay. Clear? But one more thing you need to notice here, whatever the sequence transformation matrix we are defined, so that is valid for line voltages and what? phase voltages, line currents and phase currents. That means, see, the primary voltage matrix, what you are written? T times the VSR. Correct or not? Clear? Suppose if you substitute here line voltages, this is also what? Line value of sequence voltages. If I substitute here phase voltages, this is also what? Phase value of sequence voltages. Okay? Clear, sir? Similarly, this is also correct. IP equal to T times what? IS. So this relation is valid for line quantities. If this is line means this is also line quantities. If this is phase means what? This is also phase quantities. That's what you need to understand. Okay? And I'll give a simple example here. For example, let's say you have a delta connected load. Let's say this is IB, IA. Now what about this IAB, IBC? Because this is AB, IAB, IBC, then what? ICA. This is how we can show. Clear? So what I can write here is, I can write IA0, IA1, IA2. These are what? Tell me. Sequence line currents. Correct or not? Sequence line currents. Okay? That is equal to 1 by 3 times 1, 1, 1, 1 alpha, alpha square, 1 alpha square alpha times unbalanced line currents IA, IB, IC. Okay? These are what? Again line currents. This is valid. Always. Okay? Now, similarly, what I am saying is, we can write IAB0, IAB1, IAB2. What is that? Phase currents. These are called sequence phase currents. Correct or not? They are sequence phase currents. Okay? AB, BC, CA is the phase currents, unbalanced phase currents. Okay? That is equal to 1 by 3 times IAB, IBC, ICA. 1 by 3 times this matrix multiplied with IAB, IBC, ICA. That means whatever the T inverse can be used for what? Converting unbalanced line currents to, converting unbalanced phase currents to sequence phase currents. Converting unbalanced line currents to sequence line currents. Similarly, unbalanced phase voltages to sequence phase voltages. Unbalanced line voltages to and sequence phase voltages. At the same time, the sequence transformation matrix also valid for voltage drop. That means this is the sequence voltage drop can be written as T inverse times unbalanced voltage drop delta Vp. So here delta V0, delta V1, delta V2, T inverse matrix you know, then delta Vp means delta Va, delta Vb, delta Vc. That means voltage drop in A phase, B phase, C phase. Okay, clear sir? So the sequence transformation matrix and its inverse is used for what? Line voltages, phase voltages, line currents, phase currents, apart from that voltage drops, but not for powers. Power calculations we cannot use it. Okay, how to do the power calculation I will explain at the end. Okay, so that's it. Now we need to see relation between line and phase quantities in star connected load. Okay, actually by default load is balanced. If you notice, load is always having balanced impedances, but supply may be unbalanced due to some disturbance in the network. Let's say this is the neutral current. Okay, now see what are the phase voltages? Phase voltages I can write like this. The standard way of defining the phase voltages are VA, VB, VC. What about the line voltages? Line voltages VAB. Phase voltage VA means corresponding line voltage is VAB, then VBC, then VCA. Okay, clear? And the next important thing is here, see if you notice one thing, line voltages and phase voltage relation for balanced system we know. For example, for a balanced system, what is line voltage? √3 times phase voltage at an angle plus 30. What about line current equal to phase current? This is for balanced system. But now supply is unbalanced. So if supply is unbalanced, positive, negative and zero sequence will coming into picture. Okay. So the simple thing is the positive sequence line voltage equal to, I am not going into the derivation, root 3 times the positive sequence phase voltage at an angle plus 30. Because positive sequence having what? Same relation with balanced phasors. Okay. Clear? And the negative sequence line voltage equal to root 3 times the negative sequence phase voltage but at an angle what? Minus 30. And zero sequence line voltage is equal to 0. That means never exist. What I can say? In case of star connection, in the line, the zero sequence component of voltage is always 0. But what about V phase not? May exist. It may 0 or may not be 0. Phase voltage, I cannot say, it may exist, but positive and negative sequence voltage definitely exist, but line value of zero sequence voltage is always 0 for star connection. And what about the relation between positive sequence line current and positive sequence phase current? They are equal. IL to I phase 2 equal. IL naught equal to what? I phase naught. Correct or not? IL naught also equal to I phase naught, but careful, it may exist. I cannot say it is definitely exist, it may exist. That's what you need to understand. IL naught equal to I phase naught, it may exist. Okay, clear? And the next important thing here is, sir, suppose if the neutral is ungrounded. Neutral is ungrounded means Zn equal to what? Infinity, something like this. Then definitely this current is 0. Neutral current is 0. But what is the neutral current strictly speaking? IA plus IB plus IC, which is equal to 3 times IA naught. So if neutral is ungrounded, neutral current 0, that means IA naught also 0. So line current and phase current both are what? 0 if the neutral is ungrounded. Suppose if the neutral is grounded, definitely zero sequence current will exist. You can't say like that. It may exist, it may not exist. That depends on the type of unbalance. Okay, clear? That's why careful with the zero sequence. Zero sequence may exist. You can comment on it will never exist when, suppose in this case. And also what? Line value of zero sequence voltage will never exist. Okay, so something like that we can comment. Okay, now that's about the star connection and the relations. Now in case of delta connected load, okay, see in case of delta connected load, again I am saying line voltage equal to always phase voltage, correct or not? So positive sequence, even what? Negative sequence, even what? Zero sequence. But don't say it will not exist, better to say it may exist. It may exist. Okay, clear? So due to what? Residual voltage, I can say. Next, what about line current positive sequence? Root 3 times phase current positive sequence, just like a balanced relation at an angle minus 30. But what about IL2? Root 3 times I phase 2 at an angle plus 30 degrees. And what about IL naught? Is always 0, but I phase naught may exist. I phase naught may exist, but IL naught is always 0 for delta connected load. For star connected load, VL naught always 0, but V phase naught may exist. So that's about star connected load and delta connected load. And the complex power in terms of symmetrical components. So generally the complex power expression we can write like this: S equal to root 3 S equal to 3 into V phase I phase conjugate. In that, real part is active power and imaginary part is what? Reactive power. But this is only valid for balanced system. Balanced system. If the system is unbalanced, this expression is not valid. So that's why for unbalanced system we have a relation like this. We can write like this. VA, that means every phase separately. VA IA conjugate. VB IB conjugate. Similarly, VC IC conjugate. In that, real part is total active power of 3 phase. Imaginary part is total reactive power is 3 phase. So this is valid for what? Both balanced and unbalanced system. Both balanced and unbalanced system. So VIA conjugate is what? Complex power of A phase, complex power of B phase, complex power of what? C phase. SC, SB. Sometimes he will ask you, what is the active power of A phase for unbalanced case? Okay, VA into IA conjugate. You need to calculate VA, IA, and VA, IA conjugate will give you PA plus JQA. VB, IB conjugate will give you PB plus JQ. And VC, IC conjugate will give you PC plus JQ. So if you add them, that is what? Total active power of 3 phase plus J times the total reactive power of 3 phase. Okay, but in terms of symmetrical components, I can write like this: 3 into VA naught IA naught conjugate plus VA1 IA1 conjugate plus VC VA2 IA2 conjugate. In that, real part is active power, imaginary part is reactive power. So these two expressions we can use for unbalanced system depending on what is available. Suppose VA naught, IA naught, VA1, IA1, VA2, IA2 given. Simple way we can draw like this. Instead of calculating VA, IA, VB, IB, VC, IC, that is a lengthy approach. This is a shortcut method. But careful, if voltages and currents are given in per unit, no, then this 3 will not come. If voltages are currents are given in volt and what? Amperes, na? That means volts and amperes, for example, then definitely 3 will come. Okay, careful. This 3 will come only in absolute system. In per unit system, this 3 will not come. I hope you understand this. Okay, 3 multiplication, root 3 multiplication, root 3 division, 3 divisions will not come in per unit system. And one more thing, line voltage in per unit equal to phase voltage in per unit for star connection. Correct or not? Magnitudes are same. Okay, clear? In per unit system, careful, that root 3 factors and 3 factors will not come at all. That's why when you convert star to delta, is the 3 factor came for per unit system? No, it will not come. So that's why, so even for complex power also, when you write for a balanced system, for example, then V phase into what? I phase conjugate. Why V phase into I phase conjugate? This is in what? Per unit. The 3 factor will not come. V phase is per unit, I phase is per unit. So that's why V phase into I phase conjugate is the complex power in per unit for 3 phase. But this 3, why? This is for absolute. By default is absolute. But when you are dealing with the per unit system, you should be very, very careful. Okay. So that's about the symmetrical components. Okay. Now the next important thing is the sequence networks. Now first we need to see sequence networks of star connected load, then sequence networks of delta connected load. Okay, so what are the sequence networks of star connected load? Directly I am writing, sir. See, we have to find out the equivalent positive sequence, equivalent negative sequence, and equivalent zero sequence. Okay, clear? But the neutral current is only what? Zero sequence. The neutral potential also what? Representing the zero sequence voltage. Correct or not? So zero sequence voltage, not zero. So that's why neutral reference for positive and negative, because there is no the neutral potential here, positive sequence 0, negative sequence 0. Correct or not? Neutral potential, positive sequence, negative sequence 0, but zero sequence will not be 0. That's why neutral difference for positive sequence, neutral difference for negative sequence, but ground reference for zero sequence. So careful about this. Anyway, the positive sequence equivalent circuit I can write like this. This is what? VA1. This is IA1 and positive sequence impedance Z1. That is nothing but what? Z star only. Okay. Tell me, is the neutral is going to influence the positive sequence circuit? No. Neutral impedance? No. Z star simply. What about negative sequence equivalent circuit? Simple. This is VA2, IA2, this is Z2, that is equal to what? Z star. And what about zero sequence equivalent circuit? Indirectly this is only neutral, okay, but we get here two terms. This is Z0, which is equal to Z star plus 3 Zn. That means this is Z star, this is what? 3 Zn. Now this is IA0 and VA0. But what about this? Ground reference, but not neutral reference. Okay, so from this what I can say, for star connected load, Z1 equal to Z2 equal to Z star, but Z0 Z star plus 3 Zn. That means the neutral connection must be considered for zero sequence equivalent circuit. This is true for generator, transformer, transmission, anything, sir. The zero sequence equivalent circuits, when you are drawing, neutral is the reference, ground is the reference, and neutral impedance will definitely influence. For example, if neutral is solidly grounded, then Z1, Z2 is what? Z star only. They are not going to change. But what about Z0? Simply Z star. So, if the neutral is solidly grounded, positive, negative and zero sequence impedances of star connected load are always same. Okay. Suppose if neutral is ungrounded, what about Z1, Z2? That is equal to Z star only. But what about Z0? Infinity. Why? Because Zn is what? Infinity. But here what? Zn is 0. That's why careful with the neutral grounding information for zero sequence equivalent circuit. Okay, this is true for what? Every equipment of power system. When you are drawing zero sequence equivalent circuit, now you must see the neutral grounding information. Okay, now next we will move on to the delta connected load. See, for a delta connected load, directly per phase analysis is not possible. So that's why you need to convert that to what? Equivalent star connection. So this is Z delta by 3. But what about the neutral? No concept of zero sequence current, IA0 0. If you show that IA0 0, the neutral must be open, correct or not? So what is Z1 now? Same, Z2 equal to Z delta by 3. But what about Z0? Infinity for delta connection. Okay, the zero sequence impedance is always infinity for what? Delta connection. Okay, that you need to be very careful. Suppose if it is a synchronous machine, sequence networks of synchronous machine. See, for sequence networks of synchronous machine, I am considering here a star connected generator with neutral is grounded through an impedance Zn. This is what the three-phase equivalent circuit. Okay, but careful one thing, the positive sequence voltage of generated Eg1 positive, otherwise simply Eg1. Okay, Eg1 equal to simply Eg. But negative sequence component of generated voltage is there, na? That is always 0, because generator is always designed to produce balanced voltages. Whenever balanced voltages are produced, positive sequence only exists. Negative and zero sequence will not exist. Simple common sense. And zero sequence component of generated voltage is always 0. That is the first thing. That's why when you are drawing the positive sequence equivalent circuit, Eg1 is there, voltage is there, voltage available. But negative and zero sequence, the generated voltages are not at all available. So based on this fact, we can draw positive, negative and zero sequence equivalent circuit. Let's see, if I want to draw the positive sequence equivalent circuit of generator, positive sequence. Okay, see how the positive sequence equivalent circuit of the generator, very simple. Let's see, there is a generated voltage, there is a positive sequence impedance, and then let's see, this is IA1, Z1, this is Eg. This is a positive sequence equivalent circuit of generator. Okay, so expression for VA1 is Eg minus IA1 Z1. Tell me, okay, is the neutral impedance came here? No. Positive, negative, circuits, equivalent circuit, neutral will not coming into picture. No matter neutral is grounded or ungrounded, network will remain same. Okay, positive sequence equivalent circuit network will remain same. Okay, now let's see here, what is Z1? Careful, Z1 means, you may say this is subtransient reactance, JXD double dash. You can say what? JXD dash. You can say what? JXD. But when we consider XD double dash, if the question is calculate what is subtransient fault current, if the question is calculate the subtransient fault current, then Z1 will be substituted as JXD double dash. If the question is calculate transient fault current, then you have to substitute JXD dash. If the question is sustained fault current or steady state fault current, then you need to substitute JXD. So that means depending on subtransient period, transient period and steady state period, the positive sequence impedance will be changing. Okay, but this is what? Same for salient pole machine and what? Cylindrical rotor. Both salient pole and cylindrical rotor machine, this conclusion is same. But if you really notice, positive sequence current is always going out of the generator, correct or not? But negative and zero sequence current will be coming into the generator, that we will see now. See, yeah, before that, for example, if you draw negative sequence equivalent circuit, what is negative sequence equivalent circuit of generator? Simple. This is IA2, this is Z2, and what about this? VA2. So VA2 is what? IA2 minus IA2 into Z2. That means originally the negative sequence current is going into the generator. If you want to write plus symbol, the original current is what? Into the generator. Because generally VA2 is what? Some value, but inside the generator voltage is not there for negative sequence. Just now we discussed generated voltage for negative sequence is 0. That's why negative sequence current is always going into the generator from the fault location. But positive sequence current is going from generator to fault location. Okay, even zero sequence current also going from fault location to inside the generator. That means negative and positive sequence currents are indirectly flowing in opposite direction, correct or not? And at the fault location, positive sequence voltage is almost 0, but negative and zero sequence voltages are maximum. That's why from there generator negative and zero sequence currents are coming. That means at a fault location, positive sequence voltage is minimum, negative sequence voltage is maximum, zero sequence voltage is maximum. Okay, and at generator location, positive sequence voltage is maximum, but negative and zero sequence voltages are minimum. That's why current is going towards the generator. Okay, anyway, so that's about the negative sequence equivalent circuit. But what is Z2? Irrespective of subtransient period or steady state period or transient period, always XD dash. This is for cylindrical rotor synchronous machine. But salient pole synchronous machine, you need to take what? Average. XD double dash plus XQ double dash by 2. This is for salient pole machine. That means Z2 for cylindrical rotor is always greater than Z2 for salient pole machine. Careful. Okay. But these expressions are same for what? Subtransient, transient or what? Steady state. Don't think that we are substituted here subtransient reactance. That's why this is only for subtransient period, and steady state period I need to take JXD. No. It may be subtransient, transient or steady state. This is what the so formulas. Okay, but one more thing, in case of a negative sequence current flowing in the stator, actually if this is the rotor is rotating in this direction, due to negative sequence current, whatever the magnetic field produced in that is rotating always in the opposite direction to what? Rotor. That means what is the relative speed between them? 2ns. I already discussed, but just remember, negative sequence magnetic field is always rotating in anti-clockwise direction, and rotor is rotating in what? Clockwise direction. That means negative sequence magnetic field and positive sequence magnetic field always rotating in opposite direction, and negative sequence magnetic field, rotor is always rotating in opposite direction. Positive sequence magnetic field and rotor is rotating always in same direction. Okay, clear? Now coming to zero sequence. Now what is zero sequence equivalent circuit? Careful, in case of zero sequence equivalent circuit, you must consider the neutral impedance, but 3 times Zn. Okay, clear? Now this is IA0, and what about this? VA0. Now that VA0 is minus IA0 into Zg naught plus 3 Zn. But what is that Zg naught? Just leakage reactance of the generator, okay? Because there is no armature reaction produced by zero sequence current. Because in a three-phase system, if you really notice, for a generator, okay, if there exists a zero sequence current here, Ia naught, there exists a zero sequence current here, Ib naught equal to what? Ia naught. What about here? Ic naught equal to what? Ia naught. So that's why the rotating magnetic field produced by this zero sequence current is always zero. That means the resultant magnetic field produced by the zero sequence current flowing in stator is zero. If there is no magnetic field, no armature reaction. That's why only leakage reactance is considered for zero sequence. That's why careful, sir. Sum of air gap flux means sum of A phase flux, B phase flux and C phase flux in the air gap with respect to zero sequence currents is always zero. Negative sequence current there, but rotating opposite direction to the rotor. Positive sequence current is there, rotating in the same direction to the rotor. That's about positive, negative and zero sequence. And careful with the neutral impedance. If neutral is ungrounded, open here. If neutral is solidly grounded, this term is what? Zero. Okay. So that's about the sequence networks of what? Synchronous machine. Now we'll see the sequence networks of transmission line. Okay, directly I am saying, sir, for a transmission line, this is the positive sequence equivalent circuit wherever it is connected. Okay, this is the negative sequence equivalent circuit, Z2. Same, equivalent circuits are same. This is the zero sequence equivalent circuit. This is positive, negative and zero sequence equivalent circuit. But what is the Z1? Z1 equal to Zs minus Zm and Z2 equal to Zs minus Zm. And what is Z naught? Equal to Zs plus 2Zm plus 3Zn. This is for what? 3-phase 4-wire network. But 3-phase 3-wire network, this Zn is what? 0. Because there is no concept of neutral. Earth is acting as a neutral. Earth resistance is always 0. Clear? So that is the only difference. But what is this Zs self impedance and Zm is what? Mutual impedance. Careful about this. And also I told you about transposal line and untransposal line. Just review that concepts as well apart from this. Okay? Clear? The next one is the sequence networks of transformer. So when it comes to a transformer, okay, the positive and negative sequence networks are same. And moreover, for a transformer, Z1 and Z2 and Z0 is equal to what? J times XL. Leakage reactance only we need to consider. Because there is no concept of armature reaction for generator due to positive or negative or zero sequence. That's why simply equal. Generally this is equal to almost 10%. Okay? Clear? And positive sequence network and negative sequence networks are what? Same. For generator, for transformer, this is Z1. Negative also what? Same, irrespective of its connection. But zero sequence equivalent circuit of transformer, you should be very careful. Okay, so zero sequence equivalent circuit of transformer is really depends on its connection and what? Neutral grounding. Okay, see, if you want to draw the zero sequence equivalent circuit, I can draw using switches. These are series switches and what? Shunt switches. This is what? Z0. Careful. Now this series switch, if it is a star side, series switch is what? Open. Shunt switch also open. SH means shunt switch. If it is star grounded side, series switch close, shunt switch is what? Open. If it is delta side, series switch open, but shunt switch close. Accordingly, we can draw. For example, I want to show star grounded delta. Have a look between two buses, star grounded delta. How it will be? This is the first thing you need to draw. Now, primary side is star grounded, series switch is closed. Shunt switch open, fine. Okay, shunt switch is open now. I can open like this. Done. Secondary is what? Delta. Series switch is what now? Open. But shunt switch is what now? Close. So how to draw that? Let's see. Shunt switch is closed, but series switch is open. Okay, that's how we can draw the zero sequence equivalent circuits of different equipments. Okay, star connected load, delta connected load we have seen, generator we have seen, transformers we have seen. Okay, so for star connected load, what is Z1, Z2, Z star, and Z0 is what? Z star plus 3 Zn. Okay, for delta connected load, Z1 equal to Z2 equal to Z delta by 3, but Z star equal to sorry, Z0 equal to infinity. Okay, for a generator, what happened? Z1 generally greater than Z2 greater than what? Zg0 or simply Z0. Okay, but Z1 equal to Z2 equal to what? Sorry, greater than Zg0. This is for salient pole and this is for cylindrical rotor. Clear? But for transmission line, Z1 equal to Z2, but Z0 is what? Greater than Z1 equal to Z2. Now if you see, approximately Z0 value is 2.5 to 3 times of Z1. 2.5 to 3 times of Z1. Okay, for a transformer, if you notice, Z1 equal to what? Z2 equal to what? Z0. Generally, which is approximately 10%. That's about sequence networks of different equipments. Now after the sequence networks, the next one is sequence diagram. Sequence diagram is very simple, sir. You can draw positive, negative and zero sequence diagram. Okay, for example, I will explain this with an example. If you want to draw the positive sequence diagram, na, just like a reactance diagram, you need to show the generator in series with what? Its impedance, generator impedance. Transformer, simple series impedance. Per unit only we are drawing this. And then transmission line, simple series impedance. And after that, infinite bus. Infinite bus is represented with an voltage source, sir. That's it. Nothing else. Clear? This is what? The positive sequence diagram. And what about negative sequence diagram? Voltage will not be there. Correct or not? So voltage is represented with short circuit. Okay, this is bus 1, bus 2, bus 3 and bus 4 is what? Infinite bus. Positive and negative sequence diagram are very, very simple. You don't need to see what is transformer connection and what is neutral impedance. Okay, but when it comes to zero sequence diagram, we should be very careful. Since the generator is what? Star connected, neutral is grounded, just Zg0. Suppose if neutral is ungrounded here, for example, then it must be what? Open here. Okay, then after that, transformer primary is what? Delta. Series switch open and shunt switch is what? Close. And then transformer impedance, and primary is what? Star grounded, series switch is closed. Clear? You should be very careful with the transformer. And transmission line is represented with simple series impedance. And after that, after the bus 3, what we have? Star grounded and delta. Star grounded means series switch is closed, and shunt switch here close, and here series switch open. Okay, here shunt switch is open for star grounded side, and this is short. Why that is short? Because infinite bus have represented with voltage source, but zero sequence voltage of infinite bus is always 0. See, this is what? The zero sequence diagram. So that's how we can draw the sequence diagram and also calculate driving point impedances for any given network. So practice questions on this, and I'm going to conduct a test till here. So with this we are finished per unit system, symmetrical components, and what? Sequence networks, and finally sequence diagrams. Okay, in the next class we will see fault analysis. Okay, so I'm going to conduct a test till here for 40 marks, 10 questions for 1 mark and 15 questions of 2 marks, and in that MSQ questions, NAT questions, MCQ questions, all the questions will be there. Okay, so that's it. I'm stopping here. Thank you.